Hey, everybody. Today we get into ballistic pendulums and rockets. Ballistic pendulums, most of you have done already, so this is not going to be too bad. Just remember, ballistic pendulums can be used to measure the speed of a bullet. Now, quick remember this. You've got to use momentum conservation when the bullet first embeds in the block. Why? Because a huge amount of energy is dissipated. So you can't just pretend that the bullet goes in here and that the kinetic energy of this block bullet system is the same as the kinetic energy here. Why? Because tons of heat is dissipated out of the system as the block literally drills through the wood to embed itself there. So we use momentum conservation, and that can give us the velocity of the block right afterwards. I'll call it V sub B, just for clarity. Once that's embedded, if we know that, now we can use kinetic or conservation of energy to convert all the kinetic energy of this block mass system into gravitational potential energy, MGH. And so at this point, you can just do, and you're right saying, wait, why is this a sum? Well, now it's the mass of the block plus the mass of the bullet, so its kinetic energy, 1/2 m mass of the block squared equals the total mass, again, times GH. And you can calculate the height that this thing is going to go. Here's a quick example. If the block has a mass of 5 kilograms and the bullet has a mass of 50 grams, and given that the block moves up a distance of 45 centimeters, what was the initial velocity of the bullet? And then the second question, how much of the energy was dissipated in this collision? So first of all, working backwards, we're going to go from the height change that we know is here. It's going to go up from here to here. We can figure out this working backwards. What do we know? MGH has to equal 1/2 times the mass of the block bullet times the velocity of the block bullet system squared. Plugging in our numbers, notice that the mass here is 5.05, 5 kilograms plus the 50-gram bullet. Not that it matters, it cancels out in this case. But we'll figure out the block bullet system was moving 2.97 meters per second after the bullet was fully embedded. Once we have that, we can use conservation momentum. The mass of the bullet times its initial velocity has to equal the mass of the block bullet system times its final velocity, which we know is 2.97. Plugging in our numbers, we can get the velocity of the bullet before it hit the block was about 300 meters per second, just less than the speed of sound. Finally, how much energy was dissipated? Well, to do that, all we need to do is compare the final energy compared to the initial. The final energy was just MGH. The initial energy was the kinetic energy of the bullet. And you'll discover a huge amount of energy was lost. 2,230 joules. That's roughly 99% of the initial kinetic energy of the bullet. So most of the energy, 99% of the energy, was converted to heat, which is part of the reason we can't use energy conservation all the way to the end here, setting the kinetic energy of the bullet equal to MGH here. So not valid. Rockets is our next topic, and rockets are fun. And this is actually where we've got to use a little bit of calculus in this part of it. But rockets are interesting, and for a large number of people, it was confusing how they work. If you look at this launch, you're like, oh yeah, rockets work by pushing off of the ground using the rocket engines. Rocket exhaust pushes on the ground, which lifts the rocket up. What's wrong with this explanation? Well, the problem is when it got further away from the ground, it may not work. Well, you can say, oh yeah, it's pushing against the atmosphere. But what happens when we get out in space? Can a rocket engine work in space? And the answer is, you betcha. How does it actually work? It works with momentum conservation. It's not pushing against the Earth. It's not pushing against the atmosphere. It works by throwing mass in the opposite direction. In this case, the exhaust gas is being pushed one way, pushes the rocket the other direction. There is one major complication, however, as you notice over here. As this rocket burns, the mass of the rocket constantly changes. That's a small problem. We'll worry about that in just a second. Got to mention this op-ed piece in the 1920s. New York Times posted this one. Everybody knows that after a rocket gets out of the atmosphere and really starts on this longer journey, the flight would neither accelerate nor maintain by the explosion of the charges that might have set it off. To claim that would, of course, be to deny a fundamental law of dynamics, and only Dr. Einstein has chosen dozen or so, or fit or licensed to do that. This Professor Goddard, with his chair at Clark College and the countenance of the Smithsonian, does not know the relation of action to reaction and the need to have something better than a vacuum against which to react. To say that would be absurd. Of course, he only seems to lack the knowledge ladled out daily in high school. Congratulations, you're having this ladled out in high school. Interestingly enough, I like the New York Times. They did do a retraction in July 1969. What happened in July 1969? If you remember, it was the first time we landed a man on the moon. I love this little very brief note in the New York Times. Further investigation and experimentation have confirmed the findings of Isaac Newton in the 17th century, and it is now definitely established that a rocket can function in a vacuum as well in the atmosphere. The Times regrets the error. The understatement of the year. I love it. So, what is the momentum when you're working with something in space? So, say for example, you're floating in space in a spacesuit, and you find yourself motionless with respect to the space station's airlocks 100 meters away. In your hand is a handheld laser meter tells you the distance is actually 97.3 meters exactly. What can you do to get yourself back to the airlock? The answer is throw your laser meter in a direction opposite to the direction you want to go. Yes, you're going to lose the laser meter, but doggone it, you'll get yourself back. Why? The answer is momentum must be conserved. Total momentum right now is 0. You're not moving relative to the space station. The laser meter is not moving relative to the space system. So the total momentum has to be 0. Afterwards, it also has to be 0. But now if the laser meter has a motion relative to the space station, what's going to happen? Your velocity is going to be equal to the negative of the mass of the laser meter over your mass. Will it be slow? The answer is yeah, it could be really slow depending on the mass of these two things and this velocity. But you should make it back to the space station. It just could take you a while as long as you've got enough air in your air tanks. So real quick analogy on this one is here's our rocket of mass m. It throws out a little bit of exhaust gas of mass dm, and it goes out with some exhaust velocity, v sub ex. All rocket engines have a certain exhaust velocity. That's the speed at which they shoot things backwards. The force on the rocket, the thrust is what we call that, can be calculated as follows. We know momentum has to be conserved. In other words, if momentum was 0 beforehand, the momentum of this moving backwards must equal the momentum of the rocket going forward. Dividing both sides by t, for no apparent reason at the moment, but trust me for a moment, rearranging it just slightly. Now, take a look at this. This side here, dv dt, is acceleration. But what's mass times acceleration? That, of course, is the net force. So what do we get here? We get this. The thrust produced by an engine, I'll call it F sub thrust, is equal to the exhaust velocity times dm dt. This is the rate it's burning fuel, how many kilograms of fuel per second it burns. How do you increase the thrust? There's two ways. Either increase the rate at which you burn fuel or design your rocket so it has a greater exhaust velocity. That's the golden rule of every rocket engineer is trying to increase the exhaust velocity. Exhaust velocities are usually measured in thousands of meters per second. For large rocket engines, they're in the 5,000, 6,000 range. But for ion engines, that's where they ionize, for example, like xenon gas, and use electricity to accelerate it. This exhaust velocity can get up into the tens of thousands of meters per second, meaning you can get a large thrust with a small dm dt. These rocket engines, or these ion engines, actually can produce more thrust without using up much mass. Now, all right, I was cheating you slightly in the previous example. I made it kind of trivial. I just assumed the mass went off here. In reality, most of the time our rocket's already in motion with some velocity v. and it has some initial mass m. So here's the momentum beforehand, before I ignite the rocket engine. And afterwards, what we end up is this. The rocket engine still shoots out some mass dm, but its velocity now will be the exhaust velocity minus the initial velocity of the rocket. You're like, what? Yeah, think about it for a brief moment. If the rocket was moving, say, for example, at 1,000 meters per second, and the exhaust velocity was 5,000, how fast is this moving relative to a stationary reference frame? It would be moving 5,000 minus the initial 1,000, or negative 4,000 relative to the Earth. Why? It was shot backwards at 5,000 meters per second from an object that was moving this way at 1,000. And now here's where the fun part comes in. The mass of our rocket actually got a little smaller. Its new mass is now m minus dm, where dm was how much exhaust fuel we just shot out. And its velocity is now a little bit larger. It's v plus dv. Still, momentum has to be conserved. So, what do we know has to be true? The initial momentum of the system, which is m times v, has to equal the momentum of these two particles over here. Now I'm going to make this one negative because I drew the velocity going this way. So negative mass times velocity plus mass times velocity. These are our other two terms here. This is the momentum of the exhaust gas moving towards the left. This is the momentum of the rocket moving to the right afterwards. Equals its whole momentum beforehand, which is just that. Multiplying that out, we get this rather hideous looking expression. Now there's a few good things to notice here. You might notice that this term right here cancels out with this term right here. Yay! And I've got mv on both sides, so I can get rid of that as well. But it still leaves us with this fairly not pleasant expression. And now I am so glad I'm doing this by video, so you can't throw things at me. In mathematics, if you ever have two d terms multiply by each other, remember in calculus we let d terms approach zero as we're doing our calculus. Well, here it is. In calculus, if you've got two d terms times each other, we simply assume that they are zero. It's called linearization. And here's where the tomatoes should come in. You might say, well, okay, Ms. Clymer, I kind of get that. They're both, approaching zero, so we can make it zero. But by that same argument, then you should say, well, wait a second. Both of these terms are also approaching zero, so both of these should be zero, and we get 0 equals 0, done. Mr. Clymer, I like the rocket equation. It's so simple. Yeah, I know. Here it is. Leave the tomatoes. You can save them for when you see me again. But if we do that, we get this. Setting the two terms equal to each other. And you might say, whoa, wait a second. I thought you moved that to the other side. Why do you still have a negative term here? Well, if you think about it, if you measured the mass of the rocket with respect to time, what would that look like? The mass of the rocket is decreasing with time. So yeah, dm dt is got to be, the slope of this graph is got to be a negative quantity. So dm dt is implicitly negative. So because this is negative, to make sure, and I know this term over here is positive, I'm going to add an extra negative sign here to correct that. You're like, Ms. Clymer, I wouldn't have seen that. Yeah, I know. Sometimes you got to think about what's happening to the mass, what's happening to velocity. Now, dv dt is a positive quantity. Now, I'm going to go ahead and integrate. Now, before I do that, I'm going to divide both sides by mass. Why? I want to get my mass with my dm term. And my limits here are going to be the initial mass to the final mass. And my limits for my velocity are going to be my initial velocity to my final velocity. If you do that, you'll end up with negative, I lost my negative sign, sorry. There should be a little negative sign right here yet. Sorry, I lost it somewhere. Gives me just simply this on this side, and v plus that on the other side. Plugging in my limits and doing the calculus real quick, you get the rocket equation. This was first derived by a Russian physicist. Oh, gracious goodness, I can't remember his name at the moment. But it's oftentimes just simply called the rocket equation, or if you're in Russia, it's named after that Russian physicist. It starts with S. I want to say Sikorsky, but it's not. Look it up if you get a chance. And it turns out the change in velocity of the rocket is just given by the exhaust velocity times the natural log of the initial mass of the rocket divided by the final mass. And this is the key. And we're going to use that in a bunch of ways. And let me just show you how it's used now. So the Saturn V rocket was used to carry astronauts to the moon. It was one of the most powerful ever built. What would be its change in velocity if it was a one-stage rocket? In other words, it just used these engines to get itself into space. The fueled rocket had a mass of almost 3 million kilograms, and its empty mass was this. Notice that almost the entire thing was fuel. Yes, basically the whole thing was a big bomb. The first stage engines had exhaust velocity of 2,580 meters per second. Not very large. They used kerosene and liquid oxygen, which were not, they were just plain big is the issue on this one. How do we solve it? Using the rocket equation, just plug and chug. Plugging in the exhaust velocity, the initial mass of the rocket with fuel, and then the final mass without fuel, and then solving it, we get this. This is how fast the rocket would have been going. This assumes, by the way, it's in space, so we don't have to worry about working against gravity. It would have a delta V of that. Notice that this is slightly problematic. We might say, well, that's a big number, Ms. Clymer. Yeah, but do you remember what the orbital velocity for low Earth orbit is? You remember we talked about projectile motion? How fast does something have to be going, roughly? How fast is the International Space Station? It's going 8,000 meters per second, which means even this largest rocket wouldn't be able to achieve orbital speeds, let alone get to the moon. So how do you fix this problem? So remember, roughly 7,000 meters per second. Here's a picture of the Saturn V rocket. There it is, and it just dropped off its first stage. Here's a view from inside the second stage. This is the first stage tank falling away. What it did was, once it used all the fuel in the first stage, it dropped it behind. It left it behind, which then reduced the mass of the rest of the rocket. The rocket engines are still burning, by the way. It's now burning hydrogen and oxygen, which burns much cleaner. So take a look at what happens here. So in reality, the Saturn V rocket had 3 stages. The first stage, its mass with fuel was 2.3 million kilograms. Its empty mass was this. The exhaust velocity we saw before was that. The second stage had a fueled mass that was that big. Its empty mass or dry mass was this, and its velocity was much larger. The hydrogen oxygen engine burned hotter and had a higher exhaust velocity. And then the third stage, this little part right here, its fueled mass was this, its empty mass was this, its exhaust velocity was that. What would be delta V for this one if we burned it in stages? So let me quick explain. What would the first stage do? Well, exhaust velocity times the total mass now is the full mass of the first stage plus the full mass of the second stage plus the full mass of the third stage. And the final mass, these two are still going to be full after we finish with this, but the empty mass of the first stage is that 131,000. And this gives us a delta V of this. Now, as soon as this is done, what happens? We're going to jettison this whole section and all of its mass once its fuel is done. It's what you just saw in the video. Now, when we burn the second stage, what happens? The initial mass is just the fueled mass of this stage and this stage over the final mass, which is going to be the, oh, I did the wrong number there. Should be 40,100. This is an old number. Plus that gives us a delta V of roughly this. Now, what happens after this stage is burned? Well, we disconnect right here and now discard this whole section, including its empty mass. And now when we burn the third stage, we get this exhaust velocity of the third stage, its full mass minus its dry mass or empty mass, gives us a delta V of this. You might say, well, that's not that much larger. Yeah, but think about it for a brief moment. First stage gave us a boost of this. Burning the second stage gave the second and third stage a boost of this. Burning the third stage gave a boost of this. What was the total delta V? It's the sum of all three of those, or 18,100 meters per second. That's substantial. That's enough to get us easily off of the Earth, um, achieves over the escape velocity of the Earth, and gets us to the moon. Now you might say, wow, wait a second, that's way too fast compared to the 7,000 before. But in reality, this is without assuming that there was any payload up here, the lunar lander, the lunar rover, all those kind of things, and not including the crew capsule and other pieces up here and the orbiter up here. You've got a lot going on. In reality, it never could achieve quite that delta V because of all the payload, but at least you can see that a multi-stage rocket can get a much larger delta V than if you simply ran it all at once and just carried around all the empty weight. There's one, and finally, I just want to take a look at one textbook problem, 130. You've got a ball of velocity v0, and it's going to collide with these two balls, 2 and 3, that are initially at rest. They all have the same mass. The question is, what's the velocity of all 3 of these after the collision? And the reason I want to do this problem is students usually panic because they're like, wait, we got 3 unknowns. Yeah. They give you one hint. Without friction acting, what happens is when these 3 collide, the 2 forces here are going to be acting along this line. Now, there's something interesting here. Here's the center of this ball. Here's the center of this ball. Here's the center of this ball. When they come in contact, this distance here is going to be the radius of this ball plus the radius of this ball. And this distance here, between the 2 balls, is just going to be the radius of this ball right here. This is a right triangle. And this is 2r, this is r. What does this angle have to be? And you should recognize, oh, wait a second. This has got to be 30 degrees here and 30 degrees here by the same logic. Each of these is 30, which means we know the direction that both of these are going to head off afterwards. And because they're heading off at the same angle, the velocity of this one, I'll call it v2, and the velocity of this one, v3, have to be exactly equal to each other because of symmetry. It's symmetric. So velocities of ball 2 and 3 should be the same. Setting, oh, there's the school bell. It's 1:30 here. Setting v1 as the final velocity of ball 1 and v1 and v2 as the final velocities of ball 2 and 3, we can now do a little bit of work. We know that momentum has to be conserved. Now, the horizontal, I should draw this out here. The horizontal momentums of these 2 things, mass times that, mass times this. The 2 horizontal components of this, along with whatever the final velocity of this, have to equal the initial momentum. So here's our initial momentum of the ball, which is mv0, v0 times the mass, equals, I'm going to call v1 the final velocity of this object, whatever it does, plus, and now I'm only interested in these horizontal components of this. Why? These vertical components of momentum for balls 2 and 3 must be equal and opposite. They must cancel out. I know that they can't have any vertical momentum because our initial mass had no vertical momentum. So I'm just going to look at their horizontal components. So m2 times cosine of 30, this section right here, going this way, and m3 times cosine of 30, its piece right here. Its 2 horizontal momentum plus the final momentum of ball 1 have to equal the initial momentum of ball 1. Rearranging that just slightly, knowing that v2 equals v3, I'm just going to make it a little bit simpler to solve and just replace v3 with v2, so it just gives me 2 times this quantity. Or you could write it, dropping the masses, just that. I'm going to assume this is a perfectly elastic collision. Why? Because otherwise I can't solve it. Even though the question didn't state it, there's no way I could think of solving it any other way. If it's perfectly elastic, kinetic energy has to be conserved. In that case, the initial kinetic energy of ball 1 has to equal its final kinetic energy, plus the kinetic energy of the other 2 objects. Rearranging that just slightly, dropping the m's and multiplying everything through by 2, and replacing v3 with v2, I can combine these 2 terms. It just gives me this. Plugging that into your Inspire. Now, I used x Oh, I use v, x, and y as my as my variables, where v is going to be the initial velocity here, x is the final velocity here, and y is the final velocity there. I get this. And this is the general solution. Believe it or not, I solved this before I recognized the fact, oh, they actually gave us the initial velocity. So I could have actually plugged in 10 here for both of these and 10 squared here. But now I can actually solve it. Negative 10 over 5. The final velocity of object 1 is negative 2 meters per second. In other words, this ball hits these two and then bounces back at that. And then this one ends up being, I can't even solve it real quick. If that's 10 over 5, 2, it's 4 square root of 3 meters per second. 1.7 times that. Let's just call it 6.8 meters per second. And the direction that both these are traveling, again, are 30 degrees, both up and down from the initial direction of that. And hopefully that'll get you started. This one was challenging just to figure out what's going on and the angles involved. Good luck with the rest of your homework. Hopefully you shouldn't have any too many problems with it. And please start on the review sheet. Our next period is our test, believe it or not, of Chapter 9. I know we're moving along. Hang in there and talk to you soon.